In this video, we look at our last type of indeterminate form. We know that we can use L'Hopital's rule whenever we have a 0 over 0 indeterminate form or plus or minus infinity over infinity indeterminate form. And we said, and that's if we are taking the limit of a quotient and the numerator is approaching 0 and the denominator approaching 0 at the same time. Or when the numerator and denominator both approach either plus or minus infinity. In both of those cases, we can use L'Hopital's rule. In the last couple of videos, we talked about a couple of other indeterminate forms. We have the product type indeterminate forms. That's 0 times plus or minus infinity. We rewrite that as a quotient so we can use L'Hopital's rule. And then we had two types of exponential indeterminate forms, 1 to the infinity and 0 to the 0. And we saw both of those. And then we saw another form that didn't really look like an indeterminate form. So we used the same technique on that, just not knowing if it was, necessary, but still applying some algebraic methods for rewriting the function that would allow us to compute the limit. Now, the final type of indeterminate form is this infinity minus infinity indeterminate form. Now, if you've got two functions that are going to infinity, if you're adding them, of course, infinity plus infinity is infinity. A very large number plus a very large number is going to be a large number. Or a large negative number minus infinity, a negative infinity minus infinity would obviously be negative infinity, because you'd have a large negative number minus a large positive number, and you get a very large negative number. But if these have opposite signs, so one of them is going to infinity and so is the other one, but then you're subtracting them, well, it really depends. Does this function go to infinity faster than this function? Well, then you might get infinity. If this function gets to infinity faster than this function, you might get negative infinity. If they approach infinity at the same rate, you might get a finite number. So usually in the textbook, whenever we have an infinity minus infinity indeterminate form, we've got some kind of quotient here and here, or an implied quotient, maybe involving some of our trig functions or expressions with negative exponents. Once you have those expressions with negative exponents or trig functions written as quotients, basically the way we handle this infinity minus infinity indeterminate form is we write it as a single quotient rather than a difference of two quotients. So I've got the limit as x approaches 1 from the right of this minus this. To check to make sure it's actually an infinity minus infinity indeterminate form, we'll look at this 3 divided by natural log of x. Now, natural log of x looks like this. When x equals 1, the natural log of x is 0. So this is 3 divided by 0. That's an indeterminate form. We know that anytime we have a non-zero number divided by 0, we're going to get plus or minus infinity for our limit. Now, since we're approaching x equals 1 from the right, the y values on the graph of y equals natural log of x are tiny positive numbers. So I have 3 divided by a tiny positive number. That's going to be a large positive number. And then over here, this 2 divided by x minus 1, well, is also going to infinity, because if x is slightly greater than 1 or 1.001 minus 1 is a tiny positive number. 2 divided by a tiny positive number is a large positive number, and then we're subtracting it. So I've got that infinity minus infinity indeterminate form. So how can I get rid of this? Well, relatively easily, actually. We're just going to find the least common denominator, which is just the product of those two denominators in this case, because they don't have anything in common. And then you multiply both expressions by the missing factor so that they have the same denominator. Now this denominator needs an x minus 1 in it. So I'll multiply by x minus 1. That's legal as long as I multiply the numerator by x minus 1 as well. So now I have not changed the value of this function. I've just written it with an x minus 1 over x minus 1. And now I'm ruling out the possibility that x equals 1, but it was already ruled out because that was undefined there anyway. And then I've got minus 2 divided by x minus 1. And the LCD was this times this. So this is missing the natural log of x. So I'll multiply by natural log of x. Do that in the denominator as long as I do that in the numerator. It doesn't change the value of the function as long as natural log of x is non-zero. And if we're approaching 1 from the right, this isn't 0. It's getting very, very close to 0, but it's not 0. So we can multiply by that, and it does not change the value of the function since x is not technically equal to 1. Now that we have the same denominators here, we can add the numerators or subtract the numerators because we're subtracting those. We have 3 x minus 3, I'll distribute minus 2 times the natural log of x, all divided by x minus 1 times the natural log of x. Now, my hope is that after doing that, I'll have either a 0 over 0 indeterminate form or an infinity over infinity indeterminate form. Let's think about it. Well, what happens as x approaches 1 from the right in that denominator? Well, x minus 1 will approach 0, and then I'll have natural log of 1, which is also 0. So I have 0 times 0, so that denominator is approaching 0. And then the numerator is, as if x equals 1, we'd have 3 minus 3, which is 0, minus 2 times natural log of 1, which is 0. So we end up with 0 minus 2 times 0, which is 0. So we have a 0 over 0 indeterminate form. And that's nice because now we can use L'Hopital's rule. So according to L'Hopital's rule, the limit of this function is the limit of the next function, where we take the derivative of the numerator and we divide by the derivative of the denominator. Well, the derivative of this expression, derivative of the constant times x is just the constant, derivative of the constant is 0. And then the derivative of -2 times natural log of x is -2 times the derivative of natural log of x, which is 1 over x. So that's our derivative in the numerator, and the derivative in the denominator requires the product rule. So this is our first function, and this is our second function. When we take the derivative of a product, we get derivative of the first, which is 1, times the second, undifferentiated, plus derivative of the second, which is 1 over x, times the first, which is x minus 1. So if I simplify, I've got the limit as x approaches 1 from the right of 3 minus 2 divided by x, all divided by natural log of x plus x minus 1 divided by x. Now when x approaches 1, this numerator approaches 3 minus 2, which is 1. And as x approaches 1, the denominator approaches, well, natural log of 1, which is 0. And then we're going to have 0 divided by 1, which is 0. So I have a 1 divided by a 0. Ooh, so that is actually one of our infinite limits because we've got a non-zero number divided by 0. So that's either going to be plus or minus infinity in the limit. So you might say, how do I know which one it is? Well, let's clear the fractions. Let's multiply the numerator and denominator by x to get rid of those fractions within a fraction. Then I have 3x minus 2 divided by x natural log of x plus x minus 1. And now, when I substitute x equals 1 into this, I still have a 1 divided by 0. So I get plus or minus infinity. And we just have to think about how this function in the denominator approaches 1. Approaches 0. Is it a tiny positive number or is it a tiny negative number? Well, if x is slightly greater than 1, then this x value is just a positive number, 1.001. Now, if I'm taking the natural log of 1, and I'm to the right of 1, well, that natural log of 1 is a tiny positive number. So I've got 1 times a tiny positive number. So this is a tiny positive number. And then if we're to the right of 1 again, 1.001 minus 1 is a tiny positive number as well. So I have a tiny positive number plus a tiny positive number, which is still a tiny positive number. So I've got a 1 in the numerator divided by a tiny positive number is a large positive number. So we get infinity. Now, anytime you get an infinity for your limit as x approaches a finite value, then x equals that finite value is a vertical asymptote of the original function. So this is a vertical asymptote of the function y equals 3 divided by natural log of x minus 2 divided by x minus 1. So that's what we get. And what was nice about it is what we did was we got rid of the infinity minus infinity indeterminate form. It became an indeterminate form that we could apply L'Hopital's rule to. And then we differentiated a number of times. And then we reviewed this concept from the first unit on limits, that if we have a non-zero number divided by 0, we either get positive or negative infinity. And we can decide whether it's positive or negative by looking at the signs of the numerator and denominator. So this numerator was 1, which is always positive, and then this denominator turned out to have to be a tiny positive value. It's approaching 0, but it's approaching 0 from the positive side. So it's going to be a tiny positive number. 1 divided by a tiny positive number gives us the positive infinity. If we had substituted x values on the other side, we may have gotten a negative answer. and then we'd get negative infinity. So x equals 1 is a vertical asymptote of this function. And as we approach x equals 1 from the right, the original function approaches infinity. And I claim that as we approach x equals 1 from the left, the original function approaches negative infinity. Okay, so that is how we get rid of the infinity minus infinity indeterminate form. If there are fractions, get a common denominator and write it as a single quotient. And usually that's the case in these problems. You want to try to write it as a quotient so that you can apply L'Hopital's rule.